Very good morning. Today we would be doing a lecture on the integration of fuzzy logic, neural network, and genetic algorithms. I'm assuming that we already have done something on fuzzy logic. We have studied neural network, and we have also done some basics of genetic algorithm. I'm Dr. Pankaj Agarwal from IMS Engineering College, Ghaziabad. Now, let us first understand why there is an importance or why there is a requirement of integration and why we are talking about integration of these technologies and how it is going to matter and how it is going to help. See, if you have studied these technologies separately, they all seem to be very powerful technologies. But at the same time, each and every technology has some its own advantages where it works very beautifully and it has its own disadvantages, right? And when we're talking about these technologies, we're also talking about that we would like to apply these technologies to some complex real world problems to solve. In order to solve these complex real world problems, at times mere single technology may not be of that useful, right? And that is why we are talking about the hybridization of the various technologies. In some cases, fuzzy logic seems to be more powerful, uh, especially when we have to deal with the uncertainties, right? And at different places, neural networks can be more useful, which talks about the learning and the training the way human does. So it talks about automation, it talks about automated learning. Similarly, genetic algorithms are very good, efficient at searching, and it's an optimization technique. So we can use these technologies somewhere and while solving these problems. And that is what is the basic purpose of this chapter. And, uh, and moreover, these habit systems are also important because the problems that we would be talking about, the real world problems, they can have varied nature of application domains. The requirements may be varied, right? So the complex domains may have different component problems and each of may require different type of processing. And that is why this habit system. So in this lecture, we would be trying to explore that how these habit systems can be useful and what are the various applications where these habit systems can be applied. Now, as we all know, that neural networks are very good at finding the patterns, learning the patterns. They are very good at learning the patterns which needs to be trained first, or which it is also good at clustering the inputs. But however, neural network are not very good at explaining that how they reach towards their decisions. We doesn't know the algorithm, we doesn't know the logic. It is just a kind of function approximation method on which it works, right? So that is where neural networks may not be that effective, where we would like to explain that how they reach to the solution, because at times we also need to look into how that procedure and how that function has built up, right? Similarly, fuzzy logic systems, they are which can reason the precise information. They are good at explaining these decisions, right? Wherever the inputs are vague, wherever there are some issues with the inputs and outputs. In that case, these fuzzy logic systems can be more useful. But again, fuzzy logic again has an issue that it cannot automatically acquire those rules the way neural network does. So there's nothing called automated learning associated with fuzzy systems. So they cannot acquire and learn those rules and can make their own decisions. So decision making is an issue with fuzzy logic. We have to embed those decisions in a hard code manner. And similarly, we all know that GAs are very, very effective search and optimization techniques. So since they are just a search technique, so we cannot apply GA alone for solving most of the problems. So we need to fuse them with some other technologies. So in all, the purpose and the objective of the entire lecture today would be these limitations of each and every technology would be the central force driving the behind the creation of these intelligent hybrid systems, right? So let us first talk something about the hybrid system, that what all things and how it can be classified. Hybrid systems can generally be classified into three broad categories. One is the sequential systems, other is the auxiliary system, and other is the the embedded hybrid systems. So let us discuss each of them one by one. The first comes your sequential hybrid systems. In sequential hybrid system, as the name signifies, we have a technology. Suppose we have one technology, then the output of that technology is used as an input to the another technologies. So there's something called pipeline-like structure. So one technology followed by another technology. Somehow, in the real world, these kind of hybridization has not proved to be very useful. It is considered to be a weak form of hybridization. So, example could be like we all know that in neural network the weights we normally take to start with, they are randomized, right? And at times this randomization of weights can be a big issue. So because every time we can have different random weights and the results can be different. So there has to be some proper way out. There has to be some systematic way of deciding these weights. So that is where we can use genetic algorithms. We can apply genetic algorithms in order to decide upon the weights, and then we can give those weights to the any kind of neural network to further proceed with. Right. Second is your auxiliary systems. Auxiliary system is quite simple, that we have a technology and we use another technology as a sub module of that technology. That means there can be, like, for example, we can use the genetic algorithms into as a sub module into my neural network solution, or a vice versa, right? So the neurogenetic system is an example in which the NN neural network employs a genetic algorithm to optimize the structural parameters, because GA is very good at optimizing those the different parameters, right? And the third technology is basically your embedded hybrid systems, like where there is a complete fusion of both the technologies. We can't say that each of the technologies is interdependent on each one of them, right? There's nothing like sequential form. There's nothing like one technology is being embedded into another technology. Both the technologies are being used as a sub-module of the another technology. So they're embedded, they're fused together, and both the technologies cannot do independently by their own. So fusion of technologies is also sometimes have proved to be very useful. So there can be different ways of doing this hybridization. Like, for example, we can endow the neural network with fuzzy capability to increase the network's flexibility to adapt to the uncertain environments, because fuzzy systems are good at handling the uncertain environments and vagueness. So we can use these fuzzy capability into a neural network to make it a fuzzy neural system or neural fuzzy systems. Right? Similarly, we can apply the neural learning to fuzzy systems to make the fuzzy systems more adaptive to the changing environments. So there can be different ways of hybriding these technologies. So let us take few examples which are known in the textbooks. One is the genetic algorithm-based BPN. That is, BPN is the back propagation learning. So we can employ the genetic algorithms to decide upon the various parameters, including weights and other parameters of the BPN, and then we can use the BPN. And similarly, we can have fuzzy BPN, where we can use we can train the we can use the fuzzy systems in order to tail the fuzziness into the environment by applying of backpropagation learning. And similarly, we can have a simplified fuzzy art map, where the neurofuzzy hybrid with recurrent networks can be also used. And we can have fuzzy associative memories. We all know that associative memories are useful ways to store the things. So rather than storing rather than storing a complete pattern which is uh, uh, which is absolutely true or false, we can start storing fuzzy inputs as well. Similarly, we can have fuzzy logic controlled genetic algorithms also. So there are different ways in which different examples of hybrid systems which are known into literature. Uh, this lecture would specifically talk about the genetic algorithm-based BPN, right? We would be doing what? We would be taking BPN as the major source of the problem-solving mechanism, but we would be using the genetic algorithms in order to decide, in order to build the weight matrix in order to see that how that randomized weight initialization is replaced by the genetic algorithm based weight determination method. So we all know that BPN, backpropagation, uses a gradient descent algorithm, right, which talks about the first order derivative of the squared error, root mean square error of the target and the calculated output. So in order to minimize this, we use what? In order to minimize this error, we are using a gradient descent algorithm, which is the most popular algorithm to be used in BPN. But the biggest issue with gradient descent is that it often gets stuck into local minima. That is, if you have gone through the neural network subject, then you would have been knowing about what is local minima and global minima problem. And this is one of the main issues of BPM. It often stucks into local minima. We often makes a conclusion by reaching to a local minima and declaring it to be the global minima. That is, you often declare a false result to be your actual result. So, so this local minima problem is one of the major issues of BPM. So this can be handled by replacing the weight determination method with GA. We all know that GA are very good at finding the solutions, optimized solutions in lesser number of iterations in a more effective way, in a more effective search. So GAs can be used, in fact, to guide this BPN in order to find the necessary weights connections rather than just the random weights. So we would be talking about this, that how this can be done. So GA-based weight determination method. So we'll be going through the different phases of GA in order to determine the suitable weights for our backpropagation learning, and then we'll be taking one suitable example also for this, right? Now each solution in GA, here the solution signifies the weights that we are going to take, right? So each of the weights, because that only weights help us in building the solution. So each of the weights would be considered as a solution string, and it will have some mechanism of determining the fitness of each and every weight, right? So that mechanism would be definitely a formula-based method. We have to have some kind of function so that we can determine numerically that what is the fitness value of my my string, that is my weights, and that is what we have learned in the algorithms. And definitely as a part of genetic algorithms, we would be dealing with high fit chromosomes, high fit solutions, and these high fit solutions would be participating in the reproduction. The rest of the chromosomes can be left over, right? The same thing that what happens in genetic algorithms based on the concept of survival of the fittest. So we are going to take these best fit solutions, we'll take it forward for the crossover and the mutation process, right? So that new offsprings can be produced, and with a assumption that it would lead to the finding of more stronger solutions. The next step would be that we have to find ways of encoding these weights, right? So the parameters which represent the solutions, that is these different, each and every different weight, we would start calling it as gene right now, because we have to numerically build up the system in a way the backpropagation requires as input, right? So each of the weights, we would be start calling them as a gene. They would be joined together in order to form a chromosome. That is, they would be all the weights, required number of weights for a given problem that needs to be solved through backpropagation would be joined in the form of a string, where each and every weight would be called as a gene, right? So let us consider one configuration so that we can have a more clear understanding of what we are saying. So suppose we have input represented through L, hidden inputs is represented through M, and suppose output represented through N. So what we are doing is we are trying to figure out, we are trying to map the entire genetic algorithm process towards what is required as input to BPN, right? So the next step is now the number of weights that would be required in order to determine the number of weights that would be required, that can be described by a formula, right? Which is called L plus of N, that is the number of your inputs and the number plus the number of outputs multiplied by the number of hidden bits. We will verify this formula also while doing the example, that whether this formula works or not, right? And weights we would be taking as real numbers, and we will also assume that each of the weight can have maximum 4 digits, because we have to limit the because we are converting everything into numerical configuration, so we need to limit the number of digits which each of the weights can be represented with. So suppose the number of digits for each of the gene for each of the weights is suppose D, and S would be called as a string of decimal values which comprises of genes, that is, which comprises of weights, right? So string would be defined as L plus of n into m into D, because each string is of, or each, sorry, gene is of D, the decimal values, the digits, sorry. So this string of whatever length we would generate, it would be generated randomly, right? This string would be generated randomly. See, again, string generation is random, but what among this random values which have been generated, which of the randomly generated solution would be more useful? That is what where the genetic algorithm is going to be used, which was missing in BPN, because we used to just take the randomly generated inputs and then we used to apply it. And once we complete the entire process, then we comes to know after say many generations that this randomly generated input was of no use, and that is what it can save a lot of efforts by applying the genetic algorithms. So initial population size will consider 2BP, which again would be definitely would be generated through random way, right? Now let us see that through an example, which so that we can have some understanding. So let us consider the number of inputs to be 2, middle layers to be 2, and the number of outputs to be suppose 2. So the formula that we can apply there also, we can easily verify that L plus of m is what? 2 plus of 2, that is 4, into, sorry, L plus of n, 2 plus of 2, into m, that is what we have defined earlier. So that would give you 8. So it can be done in this way also, L into m, right, plus m into n. That is how we configure our any neural network configurations, if you have learned through them. Now each of the digits, suppose the digit length we have taken over here is D, is equal to 5. So each chromosome would be of what length? 8 into 5, that is 40, right? Where we would have 8 weights. We would have total of 8 weights, right? And since each of the weight can be of digits 5, so the total chromosome length could be maximum of suppose 8 into 5, 40. Fairly simple, right? Now this is just the network which can be assumed based on what we have considered the number of inputs, middle layer and the output layers, right? So we have 2 inputs, we have 2 hidden, and we have 2 output layers, right? So next, let's take the example so that we can talk about a working example also. So suppose the gene that we there would be what, 0 to 7, that is 8 genes. So each of these gene is nothing but a weight, mind you, right? And suppose that each of the weight can be suppose we have considered randomly generated. Suppose this is one weight, right? This is one gene, this is another gene. These are all randomly generated numbers, right? These are all randomly generated numbers. So this entire string would be called as a chromosome. Chromosome biologically means nothing but a combination of genes in some order. Similarly, let's take this is gene 1, sorry, chromosome 1, and this is chromosome 2, right? So next, let us do that how we are going to extract the weights, because we have entire string of length 40 which has been generated randomly. So we can always use a random number generator computationally in order to generate a string of 40 comprising of randomly generated weights. But the problem is, or the issue would be, that how we are going to extract the weights, how we are going to extract all those 8 weights out of that completely randomly generated string. So that is what we have to decide upon a way out, right? So let suppose X1 to XD, they represent a chromosome as presented beforehand. And let's that X, K, D plus 1, I'll come to this, they represent the kth gene in the chromosome. You'll come to know through an example that would help you in order to understand these formulations. So what we have done is, so the actual weight WK would be represented in this manner, right? Right. So I'll take an example in order to see that how this looks and how this can be used. For example, let us take a chromosome A that we have decided or that we have defined earlier, right? So we extract the weights from the 8 genes. How? So see, the entire string of 40 has already been generated, suppose, for example, right? Which was nothing but we took an example beforehand. So that was a 40 digits were there. So that would be one random entire string that we have as an input. Now, out of that entire 40 digit string, then we have to extract the 8 of the genes, which would be represented for, or which would be used for a network as an input to the backpropagation. So suppose how do we extract gene 0, which was nothing but 8, 4, 3, 2, 1. So how it has been extracted is like we have the value of k is equal to 0. That is, we're talking about the 0 gene, and the d, that is length of each of the string, is suppose each of the gene is 5 that we've already taken. So x k d plus 1, which becomes d is what, 0. So k is 0, so it becomes k1 x1, suppose, right? So x1, which comes out to be what condition? 5 is less than or equal to x1. X1's length is what? X1's x1, that is the first string. The first digit of this particular gene is what? 8. So x1 is 8, which is less than or equal to 9, right? So this can be used as what? So hence the weight that we need to extract out of that is the W0, the first weight that we need to extract, that would be your what? That would be the second, leaving the first component, that is 8. The previous component was uh, the previous component was what? See, the string was 8, 4, 3, 2, 1, right? And we have extracted 8, suppose. So 4, so we need to extract what? 4, 3, 2, 1. So what we have done is 4 into 10 to the power of 3, right? That is the highest length of the digits that has to be used. An exponent would be 3 here, right? In the decreasing order. Then the third, the second, that is the third, will be taking 3, 10 to the power of 2, then 2, and then 1, right? And then we divide it by the highest exponential digit that we have used in the string, that is 10 to the power of 3. That is how the formula has been decided, right? So by calculating this, the value which comes out to be suppose 4.3. So this would be declared as what? The weight 0, right? We can have our own formulation in order to extract the different weights out of these chromosomes. So similarly, for gene 1, suppose that is, now we have to extract, suppose second weight, that is the weight 1. So the string is suppose 4, 6, 2, 3, 2, right? So again here the k is 1 now. Initially the k was 0 and the d is 5. So it follows a rule where x6 is what? We're talking about the fourth, this number 4. X6 is suppose 4 over here, because this is what? The sixth digit in the chromosome, right? This is the sixth digit that we are talking in the chromosome. So it is which is equal to 4, which is less than or equal to 5. So this follows our defined procedure. So in order to get this, again we would be applying the formula that we have defined above, and then we can easily, that is W1 can be again the second digit is 6, then 2, 3, and then 4. Then divided by the 10 to the power 3, which comes out to be this value. So minus 6.2 would now be declared as weight 1. And similarly, rest of the weights in the form of genes we're talking about, these can be calculated in similar way, right? So gene 2 means weight 2, suppose gene 3 again is weight 3. Similarly, so we would have total of 8 weights that would be that we would be extracting from the various genes from our chromosome. So this is just a formulation, mathematical formulation, which can have a different ways of formulating this, right? So next is your the fitness function. See, once So what we have done is we have extracted the weight values from our chromosome, defined chromosome, which was randomly generated. Now the thing is, now since these weights have been extracted, so we need to understand how fit these weights are, how fit the entire chromosome was, right? So we have to define the fitness function. So let us assume that we have input output. Given these input output pairs where we have two inputs and the two target values, so the input output target pair can be represented in this manner very simply. So now what is required is a set of input pairs has been given to a problem P to be solved here, right? So next, what is required is we first randomly generated the initial population P0 of size 40, right? And let C1 to C40, 0 representing the first gene, right? 0 representing the first weight or a gene. It represents 40 chromosomes of population P0, right? Sorry, 0 representing here is the first population set, right? So we would have similarly, we would be generating how many populations? One by one, we would be generating a populations of total for 40 population 40 population generations. So one generation will have all the chromosomes, and once we would be finding the fitness of each and every chromosome, then we'll move on to the next generation with 40 chromosomes. Again, we would be evaluating the fitness of each chromosome in order to find stronger solutions by applying the various reproduction and the crossover method. And then similarly, we would keep on going from one generation to another generation till we achieve convergence stage. So we will talking about how that convergence can also be achieved, right? So let us also assume that the weights corresponding to the zeroth population, that is the first population set, is represented this way. And the weights which are extracted from each of the genes would be represented in the form of Ci for the zeroth population, right? So these are the representation that we would be using for the example. So for a fixed weight set Wi, the BPN is trained for all the input instances given, that is the 3 input output pairs given, right? So the next is next we would do let us also let's suppose this output 1 2 3 are calculated. So let us define the formula for output also. So the error, so at every point of time we have what, a target value, and we have what the output value, suppose. So we had 3 inputs and 3 outputs, right? So we had three targets and 3 outputs. So we would be first calculating the square root mean square for each of the 3 inputs. So there would be 3 errors, E1, E2, E3. The calculation is fairly simple, that can be understood. That is target minus of output. Similarly, target minus output for the second second input, or the second, this first input corresponding to the first input, second input. So because we have pairs of input, right? So similarly, we have 3 weights. We have calculated the root mean square by doing what? We calculated what? We added up all the errors, then we found the root mean square, right? And then in order to calculate the fitness, what we did is whatever error we calculated, it was taken 1 by E. So this 1 by E would be considered to be as the fitness for a chromosome 1 of for the initial population, or for any population I, right? So each and every chromosome would be evaluated in terms of this fitness value, and then we would be analyzing the various the chromosomes, so various solutions which are there, which can be the probable cases for considering as input to the BPN. So we would be then selecting the more fitter chromosomes, and then we would take it to the further generations in a quest to find a very fit chromosome, right? The similar way that we used to do for finding the most optimal answer in while applying the genetic algorithms. Now next is your so this is how the architecture may visually look. We have the set of chromosomes, 40 chromosomes represented in the same manner. Then we would be extracting the weights. Then we would be extracting weights. We would be finding. We would be applying the various genetic operators here in order to extract the weights. We would be applying the back propagation. Then we would be getting the error. We would be calculating those errors. Then we would be calculating the fitness value. We will go through an example in order to understand how the entire process takes place. Uh, rest we would rest would be your reproduction phase. In this phase, the mating pool is first formed before the parent and the chromosomes can reproduce to deliver the offspring. Because once I have generated the chromosomes, then I have to make them go for the reproduction phase where we can get the newer or the better solutions. Rest of the things we will do in the next lecture from here on. Thank you for now.